Good morning, and depending on when you're watching this, good afternoon, good evening, or good night. I'm your Calc 1 instructor, and today we're going to go over section 4.1 in the Stewart Calculus textbook, Maximum and Minimum Values. By now, you should have watched the short video by Patrick JMT providing an intuitive introduction to the idea of local maximum and minimum values, collectively referred to as local extrema. Now we will provide the mathematical definition of these terms and their absolute counterparts. Let's start with local extrema. For the following, let C be a number in the domain capital D of the function f. Then we say that f of C is a local maximum value of f if f of C is greater than or equal to f of x whenever x is near C. That is, for all x in some open interval containing C. Similarly, we say that f of C is a local minimum value of f if f of C is less than or equal to f of x whenever x is near C. Now, as you saw in the last video, being a local maximum is not necessarily the same as being the greatest value the function attains. In Patrick JMT's graph, because of the end behavior he drew, his function has no greatest or smallest value, though it has multiple different local maximums and different local minimums. On the other hand, in my graph of the height of the rock thrown on Mars, we see that the maximum height attained by the rock is also a local maximum value. So let's introduce definitions for absolute maximum and minimum values. They are exactly what you'd expect. We say that f of c is an absolute maximum value of f if f of c is greater than or equal to f of x for not just x near c, but for all x in the domain D of the function f. Similarly, we say that f of c is an absolute minimum value of f if f of c is less than or equal to f of x for all x in the domain D of the function f. So the absolute maximum value is just the greatest, or you might think of it as the highest value attained by the function, and the absolute minimum value is going to be the smallest or the lowest value. So again, we see that in Patrick JMT's graph, there is no absolute extrema. There can't be any value of the function that is greater than or equal to every other value that the function attains, because the limit as x goes to negative infinity of f of x is positive infinity. And similarly, there cannot be any least number that the function attains, because the limit as x goes to infinity of f of x is negative infinity. On the other hand, in my graph of the rock's height, there is an absolute maximum value. The maximum height of around 30 feet we found earlier. There is also an absolute minimum value of 0 when the rock is at ground level. Now it is natural to ask under what conditions functions have absolute maximum and minimum values. Take a moment and pause this video to sketch some graphs. Try to draw some graphs that have both an absolute maximum and minimum value. Try to draw some graphs that only have one, and try to draw some graphs that have neither. See if there is any pattern that you notice. There is a famous theorem that provides a partial answer to this question, the Extreme Value Theorem. It states that if f is a function that is continuous on a closed interval from a to b, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in the closed interval from a to b. For example, consider the following graphs, all of which are continuous and defined on a closed interval. In the graph on the far left, we see that both the absolute maximum and absolute minimum occur in the middle of the interval. In the center graph, the absolute maximum occurs in the middle of the interval at the point C. However, the absolute minimum occurs at the right endpoint of the interval. In the right graph, we see that absolute extrema need not occur at unique points. There are two numbers, C1 and C2, such that both f of C1 and f of C2 are the greatest value the function attains. Note that there are two assumptions in the extreme value theorem. One, that f is continuous, and two, that it is defined on a closed interval. What if we don't have these? In other words, what if f has a discontinuity? Or what if f is defined on an open interval? Take another moment to pause this video and try to draw some graphs that fail the extreme value theorem in this way. Do they all have absolute maximum and minimums? Here are some examples to show that if a function does not satisfy the hypothesis of the extreme value theorem, it need not have absolute maximum or minimum values. The graph on the left is that of a discontinuous function, and though it has a minimum value, f of 2 equals 0, it does not have any maximum value. The graph on the right of a continuous function on an open interval has neither a maximum nor a minimum. Now, the extreme value theorem answers quite well the question of when a function has absolute extrema, but it doesn't tell us at all how to find the extreme values. I'm reminded now of an old joke. A mathematician, an engineer, and a chemist are all staying at a hotel for an academic convention. While they are sleeping, the hotel catches fire, waking them all up. They quickly get to work. The chemist starts going through the household chemicals in their room, trying to whip up a makeshift fire extinguisher. The engineer sees that they cannot escape through the door, so starts tying blankets together, trying to rig some way for them to escape out the window. The mathematician looks about him, exclaims, "A solution to this problem exists," and then promptly goes back to bed. I can already hear all of your laughter. The point is, sometimes in mathematics, knowing a solution exists is the best we can do. And that is all the extreme value gives us, that a solution exists. But we can do better. We can find what the extreme values are. We will need another definition first before we can move on. A critical number of a function f is a number c in the domain of f, such that either f prime of c equals 0 or f prime of c does not exist. Why do we care about this definition of critical numbers? Let's look at some of the graphs we've already seen, as well as some new graphs, and try to figure out why. Looking at the first graph in the top left corner, notice that C and D, the locations of the maximum and minimum, respectively, are both critical numbers. The graph has horizontal tangents there, so f prime of C and f prime of D are both 0. Notice that in addition to being absolute extrema, these are both local extrema as well, tops of hills and bottoms of valleys. Looking at the top left graph, the second one, the only critical number is x equals 1, because f prime of 1 doesn't exist, because the graph has a jump discontinuity there. Turning now to the bottom left graph, that of y equals x cubed, the only critical number is x equals 0, because we can again see that the tangent line is that of a horizontal line there. Looking at last at the bottom right graph, the only critical number is again x equals 0, because here the derivative doesn't exist. There is a kink at x equals 0. This time, absolute value of 0 is both an absolute minimum value and a local minimum value. Now, taking a minute and looking over these, is there any pattern that we can notice? It certainly can't be that every critical number is the location of an absolute or local minimum value, because the second and third graphs both have critical numbers that are neither max nor mins. Are any local maximum or minimum values located at non-critical numbers? No. Every local extreme value is located at a critical number, although the opposite is not true. This is the content of our next theorem, Fermat's theorem. If f of c is a local maximum or minimum value of f, then c is a critical number of f. How does this help us find absolute extrema, you ask? We combine Fermat's theorem with the following observation: that absolute extrema are either also local extrema, as in the case of the first or last graph, or they occur at endpoints of an interval, as is the case with the second graph where we have the point of discontinuity. This provides us with the following method of finding absolute extrema, which we will call the closed interval method. So, to find the absolute maximum and minimum values of a continuous function f on a closed interval from a to b, we do the following. First, we find the values of f at the critical numbers of f in the open interval from a to b. Then we find the values of f at the endpoints of the interval. In other words, we will calculate f of a and f of b. And then we just compare all of these. The largest of the f values that we have found is going to be the absolute maximum value, while the smallest of these values is going to be the absolute minimum value. Now I'm going to turn you back over to Patrick JTM. He'll give you an example of finding critical numbers, as well as an example of using the closed interval method. For now, here is a fish, the ancient coelacanth, a living fossil. Now be sure to like, comment, and subscribe.